Alright, so first semester, what was our focus? Derivatives. Okay, what did derivatives give us?
Rate of change.
Rate of change. Oh, not just a rate of change. What kind of rate of change? Instantaneous rate of change, right? Because before we've been able to find average rates of change or average slope, but derivatives allowed us to find an instantaneous slope and instantaneous rate of change, which was really helpful because there are lots of different real-world applications where things are changing due to time, and we want to know different things, the rate of change, at a particular instant. So it's a powerful tool that allows us to do a lot of stuff. The counterpart of that, which is what basically we're going to spend the rest of this semester doing, is integration. Okay, and is going to allow us to find area, which seems straightforward enough. But let's look at why it might be helpful to find. So it says, on a certain stretch of highway, Mr. Moore puts on cruise control and drives 70 miles per hour for 1.5 hours. Sketch a graph of Mr. Moore's velocity on this stretch and then find the total distance covered during that time. So what's happening with our velocity here? It's not changing, so it's another way to say that. It's constant, okay? So if I were to draw the graph of that, which is what it asks us to do first, what would that graph look like?
Straight line, horizontal.
All lines are straight. But yes, a horizontal line. We're okay with that. At what? 70. Yes? So this is at 70. This represents my velocity. Yes? Which means that my x-axis represents what? Time. This, no, maybe. So we're going, and we're in hours, so 1 hour, 2 hours, 3 hours, so forth. Yes? So far so good? Alright, then the next thing it asks us is find the total distance traveled. So speed is a rate. Yes? And how do we find rates? Just in general.
Divide them by time. Or like you take something that's changing and divide it by time.
Okay, what's the something on top? If I'm talking about speed.
Oh, distance.
Distance, right? So to find average, right? Because again, we're talking about something that is constant here. So it would just be, we can just take it by taking our, so rate equals the distance divided by the time. Yes? Now, if it wasn't a nice, pretty straight thing, then yes, we would have to take the derivative and there would be those involved. But for us, this is pretty constant, okay? But we're looking for our distance, yes? So how would I isolate my distance in that equation?
Multiply by time.
Okay, so distance is going to equal rate times time. Okay, what is our rate here? 70
miles an hour.
Okay, and what's our time?
1.5 hours.
Okay, so 1.5 hours. So then what are we left with?
105 miles.
105. And we are in miles. Because notice that our hours would reduce. Yes? And so 1.5 would be approximately like here. Yes? Alright. So if I have this graph, okay, how would I represent the 105 miles graphically?
The area underneath 70 over to time, like over 1.5.
Why?
Because that would be rate times time.
Okay, so my rate was my velocity, so that's going to be my height. My time is my length. So if I'm multiplying those two things together, we're going to get an area of a rectangle. rectangle?
Mm.
Which makes sense because an area is length times width, so that's what we found. That was our area. We're all okay with that. Okay. So let's look at a slightly different problem. See if it still works out. So Mr. Moore's son is riding his bicycle with a velocity given by the following function. So is our velocity constant this time? No, it's changing. Where v of t is in miles per hour and t is in hours. Sketch a graph of the velocity and then find how much distance was covered over a 3-hour time period. Do we think we can still use the same process though? Potentially.
Yes.
Right? Yeah. We might just have to use maybe a different formula, okay? But our distance is still going to be represented by our rate times our time. And because I'm graphing our rate and our x is our time, we're still looking at the area of whatever we get there. Are we okay with that? So, what is that graph going to look like for our velocity?
Excuse me?
Yes.
Can I have Aiden for dismissal, Tarang?
Sure.
Thanks.
Wouldn't it be a
What's the graph of 5 plus 6x look like? Yes. So it's going to be a line that has a slope of 6 and a y-intercept of 5.
5.
Are we all
Five.
okay with that? Yeah? We're just graph basic stuff. So, and have an intercept, we'll say that this is 5. Okay? And then I have a slope that goes out. So my line will look something like that. Yes?
Yeah.
Do we care about the negative half of my graph?
No.
No, because we aren't going negative. So I drew it just so we can kind of see the whole line, but we really only care about the part that is to the right. So again, our y-axis is representing our velocity. Our x-axis is representing our time. We are again in hours. So I have 1 hour, 2 hours, 3 hours. Yes? And we said that it should follow the same format. That I'm still looking for the area that has been produced from under my velocity graph. Yes? But do I have a rectangle this time?
No.
No, what do we have?
A triangle and a rectangle.
Which is also called a
Trapezoid.
trapezoid. Yes. So you do have a triangle and a rectangle. And like it wouldn't be the end of the world for you to find the area, like separating those out. However, we're going to need to remember our trapezoid area formula later on in this section, so it's helpful if we just go ahead and review it now. Do we recall what the area of a trapezoid is?
No.
Okay. Well, it's a good thing we're remembering it. So remember that a trapezoid is a little bit different than like a rectangle or a square in that it technically has 2 different bases. So like I can't just say length times width because the top base, or like in this case my bases are side to side, they're different. So what we do instead is we say base 1 plus base 2 divided by 2 times the height. Does that sound vaguely familiar? Maybe. It's been a little bit since some of us have had geometry. So in our case, like I said, we're used to seeing our bases like this, right? Like that's just our standard. We see the bottom base is on the bottom, and then the top base is vertical of that. But notice that our shape here has been like tilted on its side. So my bases are going to be along the y-axis and then along this line at time 3, which then means that my height is technically represented by the length along my x-axis. But my formula still works the same way. Are we okay with that? Just our orientation has been flipped. So, with that in mind, and because our distance is going to equal our area, okay, we want to plug into this formula. So, what is the length of my base 1?
5.
Okay. What is the length of our base 2?
30. Not 30.
times 3. The only thing is that I want to do 6 times 3
Plus 5.
plus 5, right? I'm plugging into here. Because basically wherever this intersects is going to be my height at that point. Does that make sense? And that line is given to me by that equation. So we do get 18, but then we add 5, so we get 23. Divided by 2. And then what's our height?
3.
3. So 5 plus 23 gives us,
28.
divided by 2 gives us
14.
times 3.
42.
And again, we would be in, you said it miles?
Dang. 42 miles in 40 hours.
He was booking it. Alright. Now, so it seems like, okay, we have this area thing, right? Pretty under control. But let's see what happens. So let's keep going. Now let's look at Jada. Jada is riding her motorcycle with a velocity given by v of t equals t squared kilometers per hour for 0 to 10 hours. The graph is shown below. What is the total distance Jada traveled after 10 hours? So again, going off of our previous 2 problems now, what should we be finding?
Area.
Area where?
Under the curve.
Ah, okay. So I'm looking at that right there, yes?
Mm-hmm.
Okay. So what formula do we have that finds the area of that shape?
We don't.
What's the issue?
It's a curve.
Oh, it's a curve. Okay, so before we've been finding the area of just like geometric shapes, which we know how to do. There are times, though, that we want to be able to find areas of things that are not nice, straight lines. And that's where we are going to need to build our way to integrals, because integrals are what are going to be allow us to find the exact area of what is underneath that shape. Now, for today, we're not there yet, so we're just going to be approximating that area instead. Are we all okay with that? So let's stick with our geometric shapes, and we'll just get a good approximation. So what shape might we use for that?
Triangle.
Okay, so I still need to go from 0 to 10. My base can be 10. So if I drew my triangle, I am pretending that's a nice straight line. Is that a very good approximation for my area?
No.
Not really. We got a whole lot of extra space there. Yeah. Which, like, again, we are approximating, so it's not going to be the exact answer. But we do at least want it to be, like, relatively close. Are we all okay with that? Okay. So if the triangle didn't work, what was the other shape that we've been using?
Rectangle.
Okay, we've been using a rectangle. Now, if I just did one big rectangle, that's not going to help much better, right? That's worse, actually, than my triangle. Agreed. Okay, but recall that we talked about a second ago, we didn't end up doing it because we wanted to practice our trapezoid, right? But we did say, oh, I can break this apart into a triangle and a rectangle. Yes?
Mm-hmm.
Like we can always break shapes up apart into other shapes, okay? So instead of just drawing like one big rectangle, what could I do instead?
You could do a ton of tiny little rectangles and triangles.
Okay, we're gonna stick to one shape, just because like start adding too many things and then it just gets a little
Do a
iffy.
bunch of little rectangles.
But yes, we're gonna try and draw a bunch of little rectangles. Now little is gonna be relative as far as for right now we're gonna pick a rectangle that's gonna be a nice size. Okay, so if I'm going from 0 to 10, how many rectangles might it be nice to draw?
7.
No.
5.
10. 5 or 10 rectangles would be nice, right? Because then all of our widths are going to be a nice, pretty number, right? With 5, each of them would be 2. With 10, each of them would be 1. Are we all okay with that? Okay. Now, notice that when we drew one big rectangle, that was really not a great approximation, yes? Would we agree that the smaller that I make my rectangles, the better that my approximation is going to be? Okay, so we're going to go with 10, because 10 isn't just like astronomical. We're not doing 50, right? But it's still enough that it's going to give us a little bit of a better approximation than just what 5 would have been. So, I have to have a width, so we decided that if I'm doing 10 rectangles, each of our widths would be 1. Agreed. Yes, no, maybe. So then how do I decide how high I want them to go?
Just like where that line intersects the width.
Okay, so, but like, where? So like technically like, this intersects it at a bunch of different places between 0 and 1, right? So like, at 1, okay. So this is gonna be hard here, but technically we'd be there pretending that it's a horizontal line. Okay. So then where would we draw it for 1 to 2?
I mean at 2.
Oh, okay, the x value is okay. And then we would go to 3 and 4 and 5. So, is it going to be exact? No. What type of approximation is this going to be? It's going to be a little bit of an over approximation. Yes? We're okay with that. But is this still closer than what our big rectangle or big triangle would have been? Yeah. So at least we're getting better. Now, do we remember what symbol we have out there that means to add a bunch of things together?
Sequence.
That is the name that we give it when we have a whole, like, when we list them as a list instead, but like, what's the thing that we can use to represent a series, which is when you add them?
Exclamation point? No.
So that's a factorial. You multiply those, not add them.
Is this summation?
It is a summation, which we use to, represented by the letter sigma. Yeah, sigma notation or summation notation. That means like to add. Okay. Which I'm preparing you because we are going to have to deal with sigma notation in this unit. So we're easing our way into it right now. So we're going from k equals 1 to 10, meaning that we're going to have 10 rectangles. And I'm wanting to add together all of the areas of these rectangles. Yes? What's the formula for a rectangle? Base times height. Okay. What's our base for all of these?
1.
1. That makes our formula very nice. Because really, I just have to add together our heights. Yes? Okay. So, like, how would I find my heights for each of those?
Just plug in 3 different numbers
Into where?
into the B and T.
Ah, which is?
T's close.
Alright, so if I plug in 1, what do we get? 1. If I plug in 2, we get 4. 3, we get 9, and then 16, 25, 36, 49, 64, 81, and
100.
go all the way to 100. Okay. So if we add all of those together, what do we get? No. It's not above 400. Nope. Closer, but no. 385. And this time we are in kilometers. Yes? So that's an approximation, agreed? Now we said that that was what type of approximation? Over approximation. Okay. Would there be another way to get another approximation? using rectangles still. How so?
Instead of going where the right side meets line, you go where the left side meets line.
Ah, so like for my last interval 9 to 10, I could make that my 9. Okay. So what's the only difference going to be from our right hand approximation to our left hand approximation?
The left hand one's going to be under approximation.
It is. For my left hand one, where would we have started? Or what would our first height have been? 0. And what would our last height have been?
80.
81, right? So really it's just going to be what? 100 off. So it would be 285 instead? Okay. So for our right approximation, I used the right endpoints of each of my intervals. For our left approximation, we use the left endpoints of each of those intervals, yes? Okay, if I wanted the midpoint approximation, what do you think we would do instead?
Take the middle one.
Take the middle point, right? I would do 1/2, 1.5, 2.5, 3.5, and so forth. We'd still be plugging those in. Or, nicer, easier way to do it would be as if I have a right approximation and a left approximation, what can I do with those two approximations?
Subtract the, or wait, no, divide them by 2.
Divide what by 2?
Just take the mean.
Take the average, so I would
Add them together.
add them and
then
divide by 2. There we go. So if I add those together and divide by 2, what do we get?
A number.
Yeah. What is it? 335. Now, for this particular graph, which of those 3 would have been the most accurate?
Middle one.
The midpoint, right? And that's because we are constantly increasing. Yes? So notice that all of my blues would have been an over approximation, all of our greens were an under approximation. So to like split those and get the difference, we take a midpoint. So our midpoint would have been the most accurate in this case. Okay? Now, sometimes if we're doing a bunch of like up and down, right? We had a different type of polynomial. The midpoint's not always going to be the most accurate. It just happened to be for this one. Are we okay with that? Okay. So now thinking about, right, we said that 10 rectangles was more accurate than if we had done 5 rectangles. Yes? So would we agree that like 25 rectangles would be more accurate? 50 would be more accurate. 100 would be more accurate. What would give us then the exact area? Bigger. What? An infinite amount of rectangles. Yes? What operation have we done in this class that allows us to send things off to infinity? Limits. So, that's how we're going to end up building our integrals, is we are going to, now it's not going to be quite this nice of a summation, but we're going to end up sending out our number of rectangles to infinity, and that's what's going to give us our actual area under the curve. Kind of how we sent our widths to 0, right, when we wanted to find the slope at the exact point, right? That's why it was the limit as x goes to 0. This time it's going to be the limit as our number of rectangles goes to infinity. But what that's going to allow us to do is to find accumulation of change. Because, which sounds kind of some big words, but we are changing, right? We looked at velocities, so that is velocities over time, and we are accumulating those, meaning that they are growing, so I'm adding up different velocities. So what that allows us to then find is the area under a curve. And that can be any curve, not necessarily a nice pretty geometric one. It can be any curve. Also some like applications, so we talked a little bit about today, is total distance We will also look at things like net change. This is also towards the end of the semester going to allow us to find exact volumes of, like, again, I know how to find the volume of a cone, right? But if I have a vase that has like a weird curve in it, I can no longer find the volume of that, yeah? So just like we can use this to find the area under things that have weird curves, we can also then take it a step further and use it to find volumes of stuff that has weird curves in it as well. Okay. So there's a lot of fun applications with it. Yes, no, maybe. So, and all of this is going to end up to be represented by integrals. So an integral symbol kind of looks like an S. But we're not quite there yet, but that's what we're building ourselves to. It's taking integrals. And if you've noticed on the board, an integral actually ends up being an antiderivative. Because if you notice, we're starting with velocity this time, right? Which is before we would take the derivative to get the velocity. Well, this time I'm starting with velocity, and we're going to try and work our way backwards. So integrals are actually the inverse of derivatives. So we're working our way backwards this time instead. Questions on any of that stuff?